All right, so let's get started. I'm Beth Nielsen, and today I'm actually going to be talking about transient storage and surface water-groundwater interactions and their influences on in-stream processes. So last week, Rob Van Kirk talked a bit about canal seepage and how that influences aquifer recharge, and that if we changed the whole idea of irrigating all of these areas in the West, that we would somehow influence our current quality of life or some of our favorite pastimes, such as fishing. Today, I'm going to talk a little bit more about groundwater surface water interactions, but at a very different scale. But first, we have to start thinking a little bit differently. I told Jeff on the way over here, none of the modelers so far has actually talked about modeling. I'm not going to show any equations, but I'm going to talk a lot about modeling. So the idea here is I'm going to start by trying to get everybody to think about all the different processes that influence what's happening in stream. And then once we do that, then we're going to talk about what happens when you introduce groundwater surface water interactions. So to begin, I'll give you some introductory and background information. Then I'll go on to tell you a little bit about some of the temperature and solute modeling I've done. And then we'll talk about the groundwater surface water interactions. So I'm actually going to start in an area where groundwater doesn't drastically influence in-stream processes. I'm going to talk first about some research I've done a number of years ago in southern Utah on the Virgin River. But first, some background information about in-stream temperature modeling. Typically, we treat streams as really nice boxes. And in these boxes, we move water one-dimensionally downstream, and then for temperature modeling, we provide for various fluxes, heat fluxes, so all of these different arrows you see here, where you have heat exchange with the atmosphere. And sometimes we'll even say, okay, there's also heat exchange with the bed. If we were looking at something like nutrients or other constituents, as we move our water downstream, there's lots of different reactions that can occur. That's what Michelle's going to talk about, I think, maybe. But at some point, 30 some odd, 40, maybe more years ago, people said, wait a second, we can't just treat these streams as boxes and that everything moves through them at the same rate. There's also this concept of transient storage. And transient storage is essentially any place that something gets hung up. And the actual definition is the combination of hyperrheic storage, which I'll define in a minute, dead zones, and other slow-moving water relative to the main channel flow. So places that stuff gets hung up and can do something different than everything else moving with the main velocity. So let's stop and talk about dead zones. Dead zones, basically stagnant areas, eddies, sometimes the bottom of pools. And this is what we're going to call surface transient storage. There's also the subsurface transient storage, which is the hyperrheic zone, which is the area sitting below the channel where water can go from the main channel into the substrate and then back into the channel. So people said, so we have to consider this. So what they did is they said, okay, we're going to create this main box, just like our old models. We're going to move everything downstream, but we're going to allow it to exchange with this one lumped transient storage box. So you have water moving downstream and whatever's in it, and then there's this one lateral transfer. Well, I decided that I needed to capture some of the effects of these transient storage zones on in-stream temperatures. Well, if you can imagine, the surface transient storage and the subsurface transient storage, they respond very differently in terms of temperature. One is exposed to the atmosphere, and the other is sitting there below the channel down in the sediments. So we split this into two zones. So we have now one main channel, a zone on the side, and a zone on the bottom. And what you get is something that looks like this. You have the main channel with all of the surface fluxes. You also have the surface transient storage with all of its surface fluxes. You have exchange between this main area and the subsurface, calling hyperrheic flux. Then you have conduction with those lower areas, and then further conduction with deeper areas. And the idea here is, if you think about all these various processes, to capture what's really happening, you have have to account for them if they're important. So looks cool, right? Yay, let's add a whole bunch of terms to our equations. But there are problems when you do this, which we'll get to. So talking about this, I'm going to talk about it in the context of a case study. And this is one of the less pretty pictures of the Virgin River. This is the Virgin River at extremely low flows during a time where they have a whole bunch of algae problems. And this is actually in 2007, but I'm going to talk about 2005 when I first did some data collection down there. And my study starts at Gould's Wash outside of Hurricane Bridge, which is CS1 or cross-section 1. And I have a second site at cross-section 2, which is right by the Hurricane Bridge, if anybody knows any of the area. And then a third site, about 16 kilometers downstream from CS1, is at Washington, above Washington Fields Diversion. In this particular stretch, there's some endangered species, and it's highly, highly managed because down there everything's about have more golf courses, and the growth has been huge. So water is a big issue down there. So in this area, we collected a number of different data types, and the idea here is when you make models complicated, you better have some data to show that you are not making stuff up or just creating good fits. So we collected a number of different data types to support our more complicated model. So in July and September of 2005, we collected weather data at CS1. We also collected temperature, temperature data in the water column, in the sediments, and in the surface transient storage zones. We also collected information at a boundary condition that included temperature and flows. We also collected some information about shortwave radiation behavior. It's the most important heat source. And then we did some tracer studies. One thing I didn't talk about is that oftentimes in these transient storage models, people dump dye in and they measure it downstream at some point, and they use those tracer curves to basically determine how these transient storage zones are working. And I'll talk about that a little bit more in the middle. One thing to note, we collected data not only in the main channel, but also in the surface transient storage zones. In terms of temperature data, at each of the cross sections, I mentioned that we collected temperatures at many locations. So 1 and 3 would represent our surface transient storage. Then 5 through 7 would be the combined effects of any sort of conduction and hyperrheic flux. And then we actually tried to isolate some sensors to get at one specific flux, the bed conduction. The tracer data we collected looks something like this. You can see that you have a nice curve, but you also have this tail. There's information in this falling limb and in the tail that help you understand some of the size and exchange rates with your transient storage zones. And this is supposed to make you think, oh my gosh, what a disaster area. We have all of our different fluxes that we added to our diagram to try to capture more of the mechanisms, right? But in doing so, we added a lot of parameters. So with more complicated models, we now have more parameters we need to estimate, which doesn't seem like that big of a deal unless you know something about trying to, by hand, tweak a bunch of parameters. So here's a list of the parameters that we have to estimate. There are ways that we can get at actually estimating and setting some of them. The rest of these are left to figure out. But the benefit of collecting a lot of data when you're doing more complicated modeling is that now we have a number of time series that represents the behaviors in each of these locations. And what's probably most unique is that we have different types of data. We have solute information from our tracer curves in the main channel and in the surface transient storage, but we also have temperature within the main channel, the surface transient storage, and down in the subsurface. And the idea is that you can use different lines of evidence to figure out whether or not your parameter estimates are reasonable or not reasonable. It's basically a way of validating what you've come up with. So, yes?
Can you go back up to the parameter list, though?
Are you going to try to match up the number of time series to the number of parameters?
No.
Okay.
I'm just looking at some of these, because some of these are looks like things you just measure rather than estimate. Like the total width of the channel is not something you want to estimate.
Very good.
See?
Well, good point. But
these coefficients maybe.
The total width of the channel, I mean, this is, if I was teaching you about calibration, I would say do not calibrate the total width of the channel.
Mm-hmm.
In this context, we set the bounds of the total width of the channel within the bounds of what was measured. We go out, we take one measurement, and we say, okay, the channel is 20 meters wide. Well, then you go downstream 100 yards. Oh, wait, the channel is 30 meters wide. And it's variable as you go. So the question is, on average, what is the best main channel width? So you do it within the bounds of what exists. Now, we actually, I'll show in a minute, use some imagery at one point to come up with a very concrete average of that width. So we knew it was representative, but who's going to have imagery to be able to do that? So you're right. What value do you set it to is the question. So remember, we're treating everything as boxes. We're simplifying reality, and that's where it becomes very complicated.
To make it simple, the physical structure of the system seems like things you could directly measure, at least at your cross-sectional points, but it's these relationships in terms of rates of exchange and processes that seem to be things that you have to empirically figure out.
Right, but you have 18 kilometers of reach, right? And that is split up into X number of sections that you are treating as completely mixed tanks. How do you set the widths of those sections?
And do you model it as a series of stepwise cross-sections?
Yeah, they're a bunch of connected together, but we only have 3 different measurements. Yeah. So moving on, we used a multi-objective calibration algorithm called MOSIM. And the idea here is that you can use multiple data sets simultaneously and say, we need to capture the behavior of these 2 different data sets together. But realizing that there's a trade-off associated, oftentimes you will match one at the expense of matching another. So for example, if you want to match the temperatures at cross-section 2, but you also want to match the temperatures at cross-section 3, there's going to be a trade-off in terms of the best fit. So in using this kind of mentality of multiple objectives and the trade-off associated with that, we went through a series of calibrations, and let's just quickly explain this plots. And within each column, you've got the temperatures at cross-section 2 in the main channel, surface transient storage, and subsurface transient storage. At cross-section 3, the same order. And then we have solute information. So this is our tracer information. And that's in the main channel and the surface transient storage. One thing to note here is that we have some data problems right here. So notice that we have data collected at 3 different depths at cross-section 2, and they behave like subsurface data would. Here, we start out fine, and then it collapses. Sand kind of moved, and my sensors were buried under about 2 meters of sand that I had to dig out, and then I replaced them again so you see better behavior. But in general, what we would say is that the gray, the model results, should mimic an average of some sort of these subsurface temperatures. And here, there are multiple sensors located that are representing the surface transient storage, and the gray should match an average of what's happening there. In the main channel, the gray should match what's happening in terms of the observations. So in this particular situation, our 2 objectives that we tried to fit were the temperatures at cross-section 2 and cross-section 3. And then the rest of these data basically say, are you mimicking what's happening everywhere else? And in terms of other constituents, well, you can see that we're mimicking what's happening in the temperature in the 2 places that we had we used in calibration. But in these other locations, in terms of the surface transient storage, we're doing a pretty good job. And even in the subsurface transient storage, we're doing a pretty good job. But this gray does not match our observations in terms of solute. So then you say, okay, well, what happens if you just look at solute? If you try to mimic what's happening in terms of solute in those zones, are you going to capture what's happening in terms of temperature? And the answer is no. So now all of a sudden, our temperature is broken and our solute's good, whereas before it was the opposite. So then the question is, can we use them together to get a better estimate of what's happening in all those different locations simultaneously? And the answer is kind of. So when you trade off between the temperature and the solute, so you have two completely different measures. You have energy and mass, and you're trying to use them both simultaneously to understand whether or not you're capturing the actual response within these different zones. While your temperatures look reasonable, your solute peaks and your solute tails, which, remember, represents the hyporheic and the surface transient storage, don't look that great. Now, this is one of the benefits of using a multi-objective calibration algorithm. When you have multiple objectives and you have a trade-off between them, there are objectively indistinguishable parameter sets that give you the error bounds associated with your model predictions. So in this case, the gray bounds now are the uncertainty associated with our parameter sets. And what used to be a really poor fit of solute, you can see now that we're able to capture within our uncertainty of our parameters, we're able to capture in general what's happening. So in our get-together last Friday, they talked about, do you have to have an estimate of uncertainty associated with everything that you do? I don't know if we ever talked about that, but this is something where in modeling I feel like understanding uncertainty is important. So as I mentioned earlier, to try to continue to minimize the number of parameters we're estimating while still having a complicated model, we use some thermal imagery and some other just 3-band imagery to look at some of the variability in temperatures. The warm, you can see the warm areas or the red areas, and the green areas are the cooler areas. And what we did is we came up with a threshold, and we said the warmest areas are what we're going to call surface transient storage, because those are stagnant areas that are going to want to warm up. And we created basically a binary, a threshold over which now all the black areas represent surface areas associated with our transient storage, our surface transient storage. And what that did is it decreased the parameter. In fact, it decreased 2 parameters because we also were able to estimate the average width over various sections. So by decreasing the number of parameters, you're increasing your parameters. So the other parameters, you're having less problems trying to estimate them. We also have looked at the use of various data types and which data types you need to use in calibration to decrease parameter uncertainty. Yes?
Sorry, with 2 parameters, can you repeat the 2 parameters that it decreases?
When we used the aerial for the thermal imagery and the 3-band imagery, we got rid of our width and the surface area of the surface transient storage, basically the width of the transient storage area. So we have investigated what data types you need to actually gather. So let's go back. So now we're thinking about, you have all these different moving pieces at this point. So we thought, well, this is a good strategy. We can take this strategy and we can apply it anywhere. So we moved to a mountain system. We came up to Curtis Creek, up at Hardware Ranch, and we thought we can do the same type of analysis, detailed analysis, collect all these different data types, and understand more about our transient storage within these systems. Well, it looks like a lovely little stream, very simple, well-behaved, but it's not. Turns out that in many mountain streams, you have groundwater surface water exchanges that are amazing. And you can exchange a lot of your water in your channel and back into the subsurface and get new water from the subsurface back into your channel to replace it. And if you think about it, think about what that does to temperatures and think about what that does to concentrations. It has a huge impact because you lose mass as you lose water and you potentially lose heat and you're getting cooler water with potentially different concentrations from your groundwater. So we went up to Curtis Creek and we did some temperature measurements initially, and we thought we were in big trouble. There's no way that we would get plus or minus 2 to 5 degrees C in very short reaches. We didn't understand what was happening. We quickly figured out that there's a lot of groundwater surface water interactions. So we subdivided these two different sections. We have the upper reach, the lower reach. The lower reach, this is an old channel. They have moved the channel, restored the channel, or not. And then this upper reach is less impacted. Note that the area right above that is actually a field that they flood irrigate. So we've done these studies during times of no flood irrigation because the flood irrigation creates some unpredictable stuff. So there's the human complexity. It makes it very complicated. So in this, we split these reaches into sub-reaches. And we did some dilution gauging. We did a series of tracer studies where you can estimate flow. And then you can also estimate mass recovery. This is all based on some kind of a method that was put together by Rob Payne, which was Mike Guseff's student, if any of you remember Mike. And we were able to basically march our way upstream and come up with flow estimates in each of our sub-reaches. And then my student did a detailed, this is Noah Schmadel's master's thesis work. He did a detailed error analysis, which is what is represented by those bars. So you can look at areas of significant gains or significant losses. So you can see that here we don't have significant differences because our error bars overlap. Here it looks like we have one. But in general, it looks like, well, doesn't really tell us much. But if you look at the net changes, there are actual significant net changes as we move along. And so the white bars are net changes in discharge, and at locations there are actual significant changes. But what's probably more interesting here is that you've also got net changes in mass, because you know how much mass you put in and you know how much mass you get back. And there are significant losses in mass. So you can use that information to look at gross gains and gross losses. How much within a subreach do you have coming in and going out? And we won't talk about situation 1 and 2, but you can look at these different values here, and you can look at and you can see that there are gross gains and gross losses that are significant occurring in many reaches. And it turns out we have a whole bunch of well information, and the water table kind of sits like this, and it pours in one side and out the other. Yes, David?
Can you explain how discharge and mass, why those would be different? Discharge and...
So discharge was calculated from one tracer injection.
Mm-hmm.
Then we were able to calculate mass recoveries at a certain location downstream. But you had to use the discharge from a previous, you have to use a discharge from a previous injection to be able to get at that mass.
So those are both of the tracer then?
Yes, but those are calculated from different tracer injections. So the idea here is that it seems that it's all simple, and it seems that water just goes in the channel and runs downstream. But in reality, we have hyporheic exchange, which is something I won't get into with these gains and losses. Part of that is due to hyporheic exchange. But we have this transfer of water as we move down these streams. And that's really important in the context of this particular project because of the fact that we are looking at what people are doing on their fields, and what they're doing on their fields can have a significant influence on the local groundwater table and how that influences what's happening in the stream next to them. And there's lots of people who've worked with me over the years, so are there any other questions?